I am Anil Kumar. Welcome to my series on exponential functions. We are going to look into exponential growth and model the bacteria population in this particular video. The question here is, following table provides the count for number of bacteria in a culture. So I have cut down on the question part because it was pretty long. But let's try to understand it. The table really provides you the values of number of bacteria after every 6 hours, right? So to start with, we have 250 as the count of bacteria, and then after every 6 hours the reading is taken, and that is the number of bacteria after every 6 hours. Based on this information, you need to answer the 4 questions. A. Model the number of bacteria at any given time. B. Predict the number of bacteria at the end of the second day. C. Determine when the bacteria count cross 100,000 as per your model. D. Explain the assumptions or limitations to your model. Right? So this is a very important question, and the uniqueness here is that the readings are being taken after every 6 hours. Now clearly it is kind of an exponential growth, so let's see what is the factor, the growth rate. So we can find the ratio to find the growth rate. So we can say the growth rate will be dividing 350 by 250. What do we get? So let's use calculator. We have 350 divided by 250, and what we get is 7 over 5. Or in decimals, 1.4. Just to confirm the growth factor, let's divide 490 by 350. Now, if we do that, which is 490 divided by 350, we again get 7 over 5, which is same as 1.4. So we say that since this rate at which it is growing is by a factor of r, so r here is equal to 1.4 times, correct? So it is an exponential growth. Since the initial population is 250, we could now write the function to represent the population at any time. So we can say that the population of bacteria at any time t is equal to initial value, which is 250, times the growth factor, which is 1.4, to the power of what? Now it is every 6 hourly, right? So we can write t over 6. Since every 6 hours it is growing by a factor of 1.4 times, right? So if I write 6 here for t, I get 250 times 1.4, it matches. And if I write t as 12, I get 12 over 6, which is 2. So square of this, we get the value. Let us check this value, right? So what we are saying is we have 250 within brackets 1.4, and the power we are writing as, let's say, 12 divided by 6. So if I do that and check the answer, we get 490, right? So 490 works for us, correct? You can also check 18 divided by 6. So we can say 250 within bracket 1.4 to the power of 18 divided by 6. So it's a good idea to check your model. We get 686, which is exactly the same amount, correct? So we see that this model really reflects the data provided to us, right? So that is the part A of this question. B is predict the number of bacteria at the end of second day. At the end of second day means 48 hours, right? That means basically we are looking for 48 hours. So for part B, the population after 48 hours will be 250 times 1.4 to the power of 48 over 6, correct? So let's calculate this answer. We get 250 within bracket 1.4 to the power of 48 divided by 6. And that is equal to, in fractions, it gives us an amount 3689 point something. We'll just write 3689. So it has 3689 bacteria after the end of 2 days, right? So in 48 hours, correct? So that becomes the solution for part B. So I hope till now things are absolutely clear. So that is the answer for part B. Now let's look into part C, which says, determine when the bacteria count crosses 100,000 as per your model. So as per the model, we'll substitute 100,000 for the population, right? And the formula is 250 times 1.4 to the power of t over 6. So we need to now find what t is. Well, let's first divide 100,000 by 250. And that gives you 1.4 to the power of t over 6. Now, 1 cancels, 25 in 100 goes 4 times, right? So we have 400 here. So we can write this as 400 equals to 1.4 to the power of t over 6. Correct? Well, you can use calculator to do the division. Also, we have 100,000 divided by 250. And that is 400. Now, how do you get t from this particular equation? That is kind of difficult. Now, you need to use logarithms to find the value of t, or you can just estimate by placing some values of t. So, we'll use logarithms in our case. So, you take logarithms on both the sides, we get log of 400 equals to, so when you take log on this, properties of logarithm is that power is now written as t over 6 log of 1.4, right? And from here we can divide this by log of 1.4 and multiply by 6 to get the answer. So t will be equal to 6 times log of 400 divided by log of 1.4, correct? So that should give us the result. So let's do it. So we'll do log of 400 divided by log of 1.4, and then we are going to multiply this by 6. That gives us 106.8. So we'll cross 100,000 after so many hours, correct? So they should be rounded higher, right? So we get time t equals to 107 hours. So let us check our result also, right? So let's check this result. So we'll just substitute t as 107. So the population we are saying will be 250 1.4 to the power of 107 over 6, correct? So what do we get? We get 250 within brackets 1.4 exponent 107 divided by 6 is equal to, we get slightly more, right? That is our approximation. So we do get 100,000, correct? So that is absolutely correct. So that is the answer for part C. Now part D here is explain the assumptions or limitations to your model. So we have assumed that this rate growth will be maintained. Right? On the other hand, we are very sure about it that is a limitation, since it will actually not be maintained, right? So because scarcity of food. As the population of these bacteria increases, they will not be able to sustain, right? So sustainability is not possible, is difficult, right? Since there is limited food, right? We are doing a culture. So when you're doing a culture in a particular unit, in that case, the food is very much limited. And so the growth will not be sustained as their numbers become so large, and therefore the model will not be increasing all the time, right? So it will be cutting off or tapering its growth, and so that is kind of the limitation for such a question. So I hope with this you understand, if you are given a data where the data is being collected at a given frequency, in that case, in the formula, we can incorporate this concept T over 6 like we have taken here to answer such questions. I hope that makes sense. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.